Welcome to Buffers and Titration. In part 1 of this unit, we're going to be talking about the common ion effect and buffers. Let's get started. So before we talk about buffers, we need to remind ourselves about the common ion effect. We had talked about the common ion effect when we talked about KSP in our solubility unit earlier in the year. But the common ion effect will just decrease the solubility of an ionic compound when a common ion is added. The decrease in solubility of an ionic compound when a common ion is added. So this would be like NaCl will dissolve pretty well in water, but once you add in more chlorine ions, then NaCl dissolves a little bit less. Alright, the first thing we're going to do is calculate the pH of a 0.08 molar acetic acid solution. And this is just a weak acid problem from our previous acids and bases unit. We have a 0.08 molar solution here, and that's going to lose some amount X, while H3O plus and the acetate ion each gain X. We have a Ka expression, that's H3O plus times C2H3O2 minus, divided by HC2, H3O2. Remember to ignore water completely because it's a pure liquid and liquids don't count. Look on your Ka, Kb chart from our previous unit. The Ka for acetic acid is 1.8 times 10 to the negative 5. So this is going to be approximately equal to 0.08. I am not going to throw any sneaky quadratic equations in here. You can check percent ionization. If you don't trust me, that's fine, but otherwise don't worry about it. So multiply both sides by 0.08 and take the square root. X is equal to 0.0012, or 1.2 times 10 to the negative third, which is the H3O plus concentration. That's what X represents. So, to find pH, that's the negative log of the H3O plus. 1.2 times 10 to the negative 3 means the pH will be 2.92. And there's your pH of just the weak acid solution. So now we have the same solution, except this time it's a 0.08 molar acetic acid with 0.1 mole of sodium acetate. And since it's in 1 liter, that 0.1 mole is the same as 0.1 molar. And since the sodium is a spectator ion, it's left out of the reaction completely. So we'll have the same thing with minus X plus X plus X. And the same thing with assuming that X is negligible. So now our Ka expression, also the same as what we did a second ago. H3O plus times C2H3O2 minus over HC2H3O2. And then plugging in the Ka that we found on our chart and the numbers that we have so far. X times 0.1 divided by 0.08. Let's multiply both sides by 0.08 and divide by 0.1. We get X is equal to 1.44 times 10 to the negative 5. And then that X again represents H3O plus. So pH is equal to the negative log of H3O plus. Since that's 10 to the negative 5, this will be 4.84. And so there's my pH. So why is the answer to B different than to A? Well, let's see. The addition of the common ion, that is the acetate, causes the acid to dissociate less. That means it produces less H3O plus. And therefore has a higher pH. The addition of the common ion, the acetate ion, causes the acid to dissociate less, which means it produces less H3O plus and therefore has a higher pH. Let's look at another problem. Find the pH of a solution containing 0.02 moles of NH4Cl and 100 milliliters of 0.15 molar NH3, and they've given me the beginning of the reaction. Remember, NH3 is a base, so it will take a hydrogen from water to make NH4 plus, and if you take a hydrogen from water, you're left with OH minus. We have 0.02 moles in 100 milliliters. So that's really a 0.2 molar NH4 plus. And we have 0.15 molar NH3. So when the reaction comes to equilibrium, we'll lose X, and gain X. This time we have Kb, because NH3 is a base, is NH4 plus times OH minus over NH3. And looking at Kb on your chart, that's 1.8 times 10 to the negative 5. It's just coincidental that the Kb for NH3 is the same as the Ka for acetic acid. So this is 0.2 times X divided by 0.15. Multiply both sides by 0.15 divided by 0.2. X is equal to 1.35 times 10 to the negative 5. And this time that X represents OH minus. So when I take the negative log of 1.35 times 10 to the negative 5, negative 5, so it's going to be 4.87. This represents the pOH because it's a base. Since you want the pH, you'll have 14 minus that 4.87. So that's going to be 9.13 for my pH. So now let's talk about buffers. Buffers are a solution, or a buffer is a solution that resists a change in pH because it contains large amounts of a weak acid and its conjugate base, or a weak base and its conjugate acid. A solution that resists a change in pH because it contains large amount of a weak acid and its conjugate base, or a weak base and its conjugate acid. Let's look at a math problem containing this. Find the pH of a buffer solution made by combining 1 mole of sodium acetate and 1 mole of acetic acid in a total of 1 liter of solution. So when I'm going to write the reaction, I'm going to start with the acetic acid, and we have a shortcut for acetic acid because this gets kind of long and cumbersome to write. So acetic acid, HC2H3O2, is sometimes abbreviated HAC. And then, using the same logic, the acetate ion, C2H3O2 minus, is sometimes abbreviated AC minus. And that'll just make the equations faster to write, because C2H3O2 is kind of cumbersome. So anyway, let's start with acetic acid. Acetic acid plus water will make H3O plus, because the hydrogen is going to go to the water, and AC minus, or the acetate ion. Notice that that's the same thing here, and that we ignored the Na because the Na is a spectator ion. If we have 1 mole in a liter of the acetate ion and 1 mole in a liter of the sodium acetate, we're looking for the pH. This becomes just like the problem we were working on earlier. Ka is H3O plus times AC minus over HAC. And just like earlier, the Ka of acetic acid is 1.8 times 10 to the negative 5. So over time, the acetic acid will lose X, the hydrogen and the acetate ion will gain X. So we end up with X times 1 over 1. The 1's cancel, so that equals X. And X, remember, represents the H3O+. So if I want to find the pH, that's the negative log of the H3O+. The negative log of 1.8 times 10 to the negative 5 is 4.74. And I'm actually going to use one extra significant figure here. Typically, I would just say 4.74, but it's going to come in relevant later when our pH changes very, very slightly. So how did you find this answer? Here I want you to pause and write in your own words, how did you find this answer? Using words, not numbers, not math, but actual words, how did you find this answer? So pause the video now and write down your own words. So hopefully something like plug the molarities into the Ka equation, solve for pH using the negative log of H+, something like that hopefully was how you found this answer. So now we're going to add 0.01 moles of HCl to the liter of buffered solution above and find the pH. So I'm going to rewrite that equation. That was HAC plus water, that's acetic acid, plus water will make H3O plus AC minus. Previously we had 1 mole of HAC and 1 mole of AC minus in 1 liter. And now we're going to add in 0.01 moles of HCl. So remember that 0.01 moles of HCl is really the same thing as saying 0.01 moles of H+. So my initial numbers have the 1 HAC, the 1 AC minus, but now also the 0.01 of H3O+. So what's going to happen when I put that H3O+ in is that H3O+ is going to react because it's a strong acid. And it's going to react, that means it's going to turn into a reactant, with the AC minus, since it's a 1-to-1 ratio, to produce HAC. So the H3O+ is going to go away completely. The AC minus, 1 minus 0.01, is 0.99. And the HAC, 1 plus 0.01, is 1.01. These are the numbers of moles, specifically, not molarity. These are all moles. Happens to be that the moles and molarity are the same in this case because we have 1 liter of solution. So let's just go ahead and solve for molarity. So that's the same thing as 1.01 m. And then divided by 1 liter is the same thing as 0.99 m. Now that I have molarity, the reaction as written is going to come to equilibrium. The 1.01 HAC will lose some amount X. H3O+ will gain X. AC minus will gain X. And so then I end up with 1.01 and 0.99. So I'm going to plug that into my Ka equation. H3O+ times AC minus over HAC. That's 1.8 times 10 to the negative 5 is equal to X times 0.99 divided by 1.01. Multiply both sides by 1.01 and divide by 0.99. X is equal to 1.84 times 10 to the negative 5. If you take the negative log of that, times 10 to the negative 5, you end up with 4.736. which is pretty close to the 4.74 that we had, 4.744 that we had just a second ago. So let's talk about how we found this answer. The first thing we did was that the moles of H plus reacted with the AC minus to make HAC. The first thing is specifically the moles, not the molarity, of H plus reacted with the AC minus to make HAC. Then we divided moles by the total volume to get molarity. Then let the reaction come to equilibrium. And what I mean by that is minus x, subtract from the reactant side, add to the product side, so that you can use the Ka equation. So then, of course, use the Ka expression to solve for H3O plus. And then the negative log of that to find pH. So the moles react with, the moles of H plus react with the moles of AC minus to make moles of HAC. Divide the moles by the total volume to get molarity. Let the reaction come to equilibrium, and then use the Ka expression. The way that I like to remember it is add an acid adds to the acid. We added H plus, and we ended up adding to the HAC. Subtract from the base. Add an acid, adds to the acid, subtracts from the base. All right, let's add 0.01 moles of HCl to a liter of pure water. How would that change if it was just a liter of pure water? Well, remember that HCl is a strong acid, so HCl will completely turn into H plus Cl minus. So if we have 0.01 moles of HCl divided by a liter is really the same thing as 0.01 molar HCl. It will all turn into H plus and Cl minus. Well, the pH is just the negative log of the H plus, so that's just plain 2. So why is this pH different than what was calculated in part B? Well, when HCl is added to water, instead of added to the buffered solution, the pH changes dramatically. Pure water is 7, and with the HCl, it changed to a pH of 2, because that HCl is the only source of H plus in your solution. But when you added the HCl to the buffered solution, there was also HAC in there, and so the pH didn't change significantly. One more part to this problem. Add 0.01 moles of HCl to an unbuffered solution of HC2H3O2 with a pH of 4.74. Same exact reaction, HAC plus water makes H3O plus AC minus. Notice here they're not giving you very much information, the pH of 4.74, but if you know that the pH is 4.74, then you know that the H3O plus is 10 to the negative 4.74. So that's 1.8 times 10 to the negative 5. It does not tell you what the initial concentration of HAC or AC minus is, but it also doesn't really matter. Since it's telling you the pH, it's telling you how much H3O plus was made, so it doesn't matter initially how much HAC or AC minus there was in the container. We just assume it reacted to make this particular amount of H3O plus. So we're going to add 0.01 moles of H plus to this solution, plus 0.01, and since it's a 1 liter, or at least since we can assume that it's 1 liter, then that's the molarity. When we add that together, we end up with 0.010018 moles per liter, so 0.010018 molarity of the H3O plus. Now what makes this an unbuffered solution is that we don't have any AC minus for that H plus to react with, so we're not going to subtract H plus from the AC minus like we did before. So let's just assume 1 liter, 0.010018 molar. So pH is the negative log of that. And that's going to be 1.999, I believe, or 2. Which tells me that the pH doesn't really change. When I added the H plus to water versus adding the H plus to the acetic acid, the pH stayed at 2. What does it mean that this solution is unbuffered? Unbuffered means it contains only the weak acid, not its conjugate base. And in this example, it's a weak acid and conjugate base, or it could also, in a different type of solution, contain only a weak base, not its conjugate acid. So since it did not contain the conjugate base, then the HCl could not react with the conjugate base. So the HCl just added to the solution it did not react with the AC minus because there wasn't enough AC minus for it to react with, because there was no buffered solution. So then the HCl became the majority, or the major, source of H plus, not the HAC like we had earlier. Alright, so those are buffer problems. Join me again next time. We're going to look at the Henderson-Hasselbalch equation. The exact same buffer problems, just a different way to do them. See you then.